Now let's see a few examples on this resource allocation graphs. First example is this. If you watch this, it is a resource allocation graph, and here the resources are single instances, isn't it? Because every resource cell that is containing only one dot, right? Or you can understand it, right? By the convention, it is a single instance graph, single instance resource type graph. And what about this one? See this. Here we have two dots, therefore it is multi-instance resource type graph. And what about this one? We have got two dots, three dots, two dots, therefore it is also multi-instance resource type graph. And okay, let's solve it first. So if you watch the first one, right, P1 has already taken R1 and P1 is waiting for R2, and P2 has already taken R2 and P2 is waiting for R1. Therefore this cycle is going to lead to a deadlock, right? So in case of single instance graphs, if there is a cycle, then it is a deadlock. Remember that. In case of single instance graphs, single instance resource type graphs, if there is a cycle, then it is a deadlock. Okay, fine. If you didn't understand it this way how to analyze it, maybe we shall go to the original method. See, if such a graph is given in your exam and if you don't know what to answer, then convert it to the table method, and I think from table method you can understand, you can easily solve it, right? So watch this one from the table instance. Let's see this. So how many processes are there? Two processes, P0, P1. And how many resources are there? Two resources. What are they? R1, R2. Oh, okay, it is P1, P2, right? The processes are P1, P2 and the resources are R1, R2, right? Now let's see what is the allocation, right? Which means how many resources are allocated to each process. So watch this. P1 got allocated R1 and then P1 is waiting for this. Okay, let's talk about only the allocation. Allocation means go to the resource type and see the arrows. See, this R1 is showing an arrow to P1. Therefore R1 is allocated to P1. So R1 is allocated to P1, right? And what about this one? It is showing an arrow from R2 to P2. Therefore R2 is allocated to P2, right? And these are the only two allocation, allocation edges, right? And therefore you fill the other entries with zeros. And what about the request matrix? The request means what is each one requesting, right? So now watch it. P1 is requesting R2, therefore I am writing it as 1. And P2 is requesting R1, which means go to the process. See, for allocation matrix, go to the resource and then write it. And for request matrix, go to the process and write it, right? So now you go to the process and write the request matrix. Now P1 is actually requesting R2, therefore I am writing it as 1. And P2 is actually requesting R1, therefore I am writing here as 1. And the remaining you fill it up with zeros, right? And now after finding it out, you find the availability. See this? Only one instance of R1 is there in this system and it is already allocated, therefore nothing is available. Similarly, only one instance is there in the system of R2 and is already allocated and therefore nothing is available, right? So R1 and R2, the availability of R1 and R2 are 0 and 0. So with this available vector, can you satisfy any of the processes? If you watch it, with this available 0, 0, you cannot satisfy either this request or this request, which means you cannot satisfy any request, right? Therefore, what can you say? There is a deadlock here. Got it? See, whenever with the available request, see, the necessary condition for no deadlock is using the available vector, you should be able to satisfy at least one process request. If you are not able to satisfy at least one process request, definitely there will be deadlock. But in case if you are able to satisfy at least one process request, it doesn't mean that there is no deadlock, because later you will not be able to satisfy other process requests. Anyway, if you are not able to satisfy even one process request, definitely it is a necessary condition for deadlock, right? So this is a necessary condition for deadlock. And moreover, now just remember this, if you have a cycle in a single instance resource type, Single instance resource type means this one. If you have a cycle in this, in the single instance resource type, that is sufficient. It is a sufficient condition. So you can write it somewhere. Cycle in single instance resource type is sufficient condition for deadlock. Not just necessary, it is sufficient. It is necessary as well as sufficient, and saying that it is sufficient is more stricter than saying that it is necessary. Obviously it is necessary and it is sufficient as well, right? Okay, that is how you can solve it. So if you didn't understand how to solve it, just write the table and you can solve it. Now let's see about this one. Again, I don't know whether it is safe or unsafe, or I don't know whether it is there is deadlock or not. Then what I do is I'll construct the tables and then I'll try to see whether I could satisfy the need with the available, right? So let me see how many processes are there in this one. 1, 2, 3. 3 processes are there. So the total number of processes in this one are P1, P2, and P3. Right? And how many resources are there? 2 resources, R1 and R2. Right? Fine. Now let's talk about allocation, right? Allocation matrix. So how can you find out the allocation matrix? Go to the resources and see to which process it is allocated. Now let's see R1. R1 is allocated to P1. Therefore R1 is allocated to P1. Let's see R2. R2 is allocated to P2 as well as P3, which means R2 is allocated to P2 as well as P3. And in the remaining elements you just write zeros, right? That is the allocation matrix. Then what about the request matrix? In order to find out the request matrix, you have to go to the processes and see the outgoing edges, right? So in order to find out the allocation matrix, you have to go to the resources and see the outgoing edges. Now in order to find out the request, you go to the process and see the outgoing edges. Let's see this P1. Now P1 and the outgoing edge is this one, right? Which means P1 to R2. Therefore P1 is requesting R2 and P2 is requesting R1. Okay, and P3 is not requesting anything. Fine. So there are no outgoing edges of for P3, isn't it? So the remaining is 0, 0, and this one is 0, 0, right? What about the availability now? Availability is 0, 0, right? So availability is 0, 0, isn't it? It is same as this one. See, this graph is same as this one, except that there is one more instance of R2 which is taken by P3. Now my question is, what can you say about this state? Now can you actually provide fulfill the requirement of any process using this availability? You cannot fulfill the requirement of any process, but then you are lucky that actually P3 does not require anything to be fulfilled. P3 is already satisfied, right? And you need not satisfy its need. Therefore P3 is very much satisfied, and after its execution P3 is going to give you back 0, 1, which means P3 is eventually going to leave R2 because it doesn't need anything else. So after some time, eventually P3 is going to release R2. Therefore you will end up getting, see this, even though your availability is 0, 0, after some time P3 is going to release the resources which it is holding because it doesn't need any more. Therefore it is definitely going to go to completion, and you are going to get 0, 1 here. Yes, once you get 0, 1, then what will be the new available? New available will be 0, 1, right? Now using this new available, you can easily satisfy the other needs. Okay, whose need can you satisfy? You can satisfy P1's need, right? Therefore once you satisfy P1's need using 0, 1, because it needs 0, 1 and you have 0, 1, then you can easily allocate 1, 0, right? I mean, you can easily get back 1, 0. So once you get back 1, 0, the new available will become 1, 1. Now using this 1, 1, you can satisfy the need of P2. Therefore you got a safe sequence. The safe sequence is P3, P1, P2, right? So what can you say? There is no deadlock here, and the system is safe as of now, and it is actually safe, right? There will be no deadlock. So the system is safe. Now what can you understand? Even though there is a cycle, right, still there is no deadlock. Therefore, in multi-instance graphs, a cycle need not necessarily mean a deadlock, which means cycle is not a sufficient condition. But okay, let's see this. Let me put it this way. Then let's analyze what happens. What I mean to say is, we have seen a multi-instance graph in which there was cycle. Just remove this edge. There is a multi-instance graph in which there is a cycle, but still that cycle doesn't mean that there is a deadlock, right? So multi-instance graphs, cycle doesn't mean deadlock. Now let's see if cycle means deadlock actually. Okay, let's see this example, then it will be clear for you. Now watch it. Now everything is same except that P3 also wants R1. So in the request matrix, P3 wants R1. Now see what happens. Available is 0, 0 and the requirement is 0, 1, 1, 0, 1, 1. You cannot fulfill anyone's requirement. Therefore, it is stuck in a deadlock. Therefore, every cycle in a multi-instance resource type graph is not a deadlock. But if there has to be a deadlock, there has to be a cycle. Okay, please note it down. I don't know whether you understood it or not. I'll just tell you this. I'll just tell you 3-4 points. You please note them down. It will be very easy, but you have to keep on reading them until you get it right. First point is, in single instance resource type, cycle is a sufficient condition. If you see a cycle, you can directly say that there is a deadlock and leave it there. You need not go here and then do all this. But in case of multi-instance resource types, right, if there is a cycle, it may or may not be deadlock, right? Therefore, cycle is just a necessary condition but not sufficient condition, which means even though you have a cycle here in the earlier graph, there is no deadlock. But later if you have the cycle again in the graph, there is a deadlock. Therefore, cycle is just a necessary condition for deadlock, but cycle is not sufficient, which means if we have a cycle, see, whenever I say it is a necessary condition, it means that it may or may not be, which means if there is a cycle, there may or may not be a deadlock, but if there is a deadlock, there will be a cycle. Okay, please note it down, or if you want me, I'll write it, right? I hope that you have copied this example. I'll just write these points here. So in case of single instance resource type, cycle is a sufficient condition, right? In case of resource allocation graph with multi-instance resource types, cycle is a necessary condition for deadlock but not sufficient. Why is it not sufficient? Is if there is a cycle, you cannot directly declare that there is a deadlock. That is why it is not sufficient, right? It is just necessary, which means without a cycle there is no way you can get a deadlock. Are you getting this? It is not sufficient because if there is a cycle, you cannot directly declare that it is having a deadlock, but it is necessary because without a cycle you can never form a deadlock in multi-instance resource type. I hope that you understood this, right? These are important theoretical points about this. Fine. Now let's talk about this question. This is given in GATE. I think it is given in GATE 94. You can read that question there. And now they are asking about, they have given you this resource allocation graph and they are asking few questions. The questions are obviously, you know them, right? Whether it is safe or not and whether there is a deadlock or not, like that. So just watch it. the same procedure, right? The procedure is same. Now I am going to try writing the allocation graph and then request graph. So how many processes are there? The number of processes here are 4, right? What are they? P0, P1, P2, P3. 4 processes are there, and the number of resources we have is 3, R1, R2, R3. Right? Let's write the allocation graph. So how did I say you how to write the allocation graph? Go to each resource and see the outgoing edges, and you go and fill the corresponding entry. Now go to R1. Now R1, if you look at it, it is showing that one is allocated to P0 and other is allocated to P1, right? Yeah. So R1 is saying that one is allocated to P0 and other is allocated to P1. So one is allocated to P0 and other is allocated to P1. That is what is R1 is showing. And R2 is showing that one is allocated to P1, and other is allocated to P2, here, and other is allocated to P3. Fine. And R3 is showing that one is allocated to P0. So R3 is showing that one is allocated to P0. Isn't it? This is the allocation graph. That is how you can fill the allocation, and just fill all the other entries as 0, 0, right? And what about the need? So in order to find out the need, what you should do is go to the processes and then see the outgoing edges. That is what they actually find the they actually get the request, right? So go to each one. Now if you look at P1, what are the outgoing edges? Only one outgoing edge, and it is going to R1. Therefore P1 needs only R1, which means 1. And what about it is P0, right? P0 actually requires one instance. How many outgoing edges are there? 2 outgoing edges, right? So one outgoing edge is here and other outgoing edge is here. So P0 requires one instance of R2, fine, and one instance of R3, fine. And what about P1? P1 requires one instance of R1, fine. And P2 requires one instance of R3, here, right? And P2 requires one instance of R3. Yes, it is really confusing, I'm not very sure whether I'm writing it right or wrong. I mean, the procedure is same, but then I don't know whether I skip some edge here or not. If I skip anything there, the answer will be very different. So if you think that I have skipped anything here, because in classroom generally students will remind me, here there is no one to remind me, right? So if I by mistake skip any edge, you please correct it in your notes, and you continue with the example. I don't know whether I'm skipping anything here. I'm trying to do my best. See this? Now P1, it is having only, P2 is having only one outgoing edge, therefore it is going to be R3. And then P3 is having 2 outgoing edges, both are going to R2 itself. Therefore it means that P3 requires 2 instances of R2. Okay, fine. And then you fill the remaining as all the zeros, right? So in case if you are getting confused while you are doing this, maybe you could put a box like this and it will help you. Okay, fine. And now we have to find out the available. So how can I find out the available? Among in all the resources, how many resources are still remaining in your hand, that is available, right? Let's see what is available. R1 is the availability is 0 because everything is given away, and R2 is available is 0 because everything is given away, but R3 there is one availability, right? Therefore if you find out the availability will be R1 is 0, R2 is 0, but R3 is 1. 0, 0, 1 is the availability. Now with this availability, can you satisfy the need of anyone? Yes. It turns out that P2 can be satisfied. Therefore if P2 is satisfied, what is that that gets back added? If you satisfy the need of P2 with this, then P2 is going to release 0 1 0, which means this is what P2 is already holding, therefore it is supposed to release, or it is going to release 0 1 0. Then what do you get? 0 1 1, right? And if this is available, can you satisfy any need? Yes. So after satisfying P2, it is clear that you can satisfy P0, because it requires only 0 1 1, right? So if you can release 0 1 1, it is by P0, then what is that you get? 0 2 2, right? Yes. Now after getting 0 2 2, can you satisfy any need? Yes. It turns out that you can satisfy the need of P3. Now if you satisfy the need of P3, what will P3 release? P3 will release 0 1 0, 0 1 0, right? Then what do you get? 0 3 2, right? And after doing this 0 3 2, right? Can you satisfy the release of anything about P1? Oh, P1's request, P1 cannot be satisfied at all. So it turned out that P1 cannot be satisfied anyway, or did I do anything wrong? Yeah, I think I did something wrong here. So when P0, okay, let me do it again. So at this point, when P0 has, when 0 1 1 is satisfied, P0 is actually releasing 1 0 1. 1 0 1, then what happens? It is actually releasing 1 1, I mean the total availability now becomes 1 1 2, right? Now using 1 1 2, can I satisfy the need of any process? 1 1 2, yes, P1 can be satisfied, not P3, right? So now P1 can be satisfied, which has the requirement of 1 0 0, right? Therefore P1, if you satisfy it, it is going to be 1 0 0, right? And therefore the new availability now is 2 1 2, right? So now using 2 1 2, can you satisfy P3? P3 is not getting satisfied. Okay, I don't know where I have gone wrong, and I don't know whether all the processes are have to be satisfied or not here. P0 is over, P1 is over, P2 is over, and if they're all over, then R2 must be 3. But why did I get R2 as 1? Let me see. If P1 2 P2 somewhere I did something wrong. Okay, let me just check it. Let me just check this diagram one more time. What is the requirement of P0, or what is the allocation for P0? P0 is allocated with one instance of R3 and one instance of R2. This is where I wrote it wrong. P0 is actually allocated with one instance of R2 and one instance of R3. Yes, one instance of R2 and one instance of R3. Just be careful. This is really confusing. I mean, you have to be very careful while you write this. Please be careful. I think others are right. And what about P1? Let me just verify it one more time. P1 has to be allocated one instance. I mean, P1 is allocated. Oh wait, P0 is allocated one instance of R1 and one instance of R3. It is right only. Okay, can you do it? Shall I leave it here? Let me see if I could finish it. Otherwise, you do it. It is really confusing for me. I mean, copying there from here. So P0 has 1 0 1, fine. And what about P1? P1 is being allocated what? One instance from R1 and other instance from R2. Yes, 1 1 0, right. And what about P2? P2 is allocated one instance from R2. That's it. Fine. And P3 is allocated one instance from R3. R2. Yes. P3 is allocated one instance from R2. Yes. And what about the need? So need is, you have to find out the need of each process by seeing the outgoing edges. Let's see the need of P0. P0 needs one instance. Yeah, P0 requires, P0 needs one instance of R2 and one instance of R3. One instance of R2 and one instance of R3. And similarly, P1 requires P1 requires one instance of R1, that's it, good. And then P2 requires one instance of R3, fine. And P3 requires two instances of R2. Yes, everything is right. Let me see this. Then where did it go wrong? Let's see. I feel that everything is right. Actually, now the time is 3 a.m. and I have been working throughout the night, and so my mind is not working completely properly. So please forgive me because I'm taking some time here to solve it. But let me finish it off. Now, what about the availability? So availability is R1 available is 0 and R2 available is 0, and what about R3? R3 available is just 1, so 0, 0, 1 is the availability, right? Now using this availability, can you fulfill the requirements of anything? Yes, you can definitely fulfill the need of P2. Now once you fulfill the need of P2, what will become available? So 0, 1, 0 will be released, right? Therefore these will be released, therefore the new availability will now become 0, 1, 1. Now using 0, 1, 1, see, which means you have already fulfilled the need of P2. Now using 0, 1, 1, you can fulfill the need of P0, right? So if I fulfill the need of P0, then what happens is 1, 0, 1 will be released, right? Then what will be new available? New available will be 1, 1, 2, right? Now using 1, 1, 2, see, P0 is over and P2 is over. Now I have 1, 1, 2. Using 1, 1, 2, what can you fulfill? Obviously you can fulfill P1, isn't it? Because P1 requires only 1, 0, 0. If I fulfill P1, then what do I get? 1, 1, 0, right? Then what do I get? 2, 2 and 2, right? So this is the new available, right? After fulfilling P1. And now using 2, 2, 2, can I fulfill P3? Yes, obviously yes. Thank God. Right? So now the safe sequence is P2, P0, P1 and then P3. See, I have taken it a lot of time to solve it, but if you do it, I think you could do it in 1 or 2 minutes. Even if I sit down and with pen and paper, if I do it, I could do it in 1 or 2 minutes, right? So don't think that it is very difficult. The only part is I am just confused in writing from here to here. Okay, that is because now the time is actually 3 a.m. right? So if you do it in normal times, it will take less time only. Okay, fine. So this is how we can solve it. So the interesting points or important points are, in single instance resource type, cycle is a sufficient condition. In multi-instance resource type, cycle is just a necessary condition, right? And every cycle doesn't mean that there is a deadlock. And here also you can see that there are lots of cycles, right? And even though there are cycles, there is no deadlock. So every cycle in multi-instance graph is not a deadlock. But then if there has to be a deadlock, there has to be a cycle. These are the important points. Okay.